Start by opening the FDTD100 Sources Import create_dataset.lsf script file. This script file calculates the fields for a radially polarized Gaussian beam. The method used to calculate the fields of the radially polarized beam is similar to the method for calculating the field profile for a Gaussian source when using the thin lens method, but instead of having a linear polarization direction, the field components are radially polarized. The fields are defined in the xy plane, so the source will propagate along the z-axis. In the section of the script shown here, the electric field data and corresponding x and y position parameters are packaged into a rectilinear dataset, then saved to a .mat file. The .mat file will be saved to your current working directory when you run the script file. Add an import source from the Sources drop-down menu. Edit the source and click on the Import Source button, which opens the file browser. From the file browser, you can choose the file type to look for, either .mat or .fld. Select the Import Data.mat file and click the Open button to load the data. Now that the data is loaded, you can see that the injection axis is fixed to the z-axis. The imported source settings show information about the center position of the field data that has been imported, as well as the wavelength if the wavelength data was specified in the dataset. Under the Geometry tab, the spans of the source are also fixed, and they correspond to the area over which the fields from the imported dataset are specified. However, the center position of the source can still be modified to shift the position of the source. The wavelength injected by the source can still be set under the Frequency Wavelength tab, and doesn't have to match the wavelength specified in the imported dataset. Set the wavelength to 0.5 microns. If injecting over a broadband range, you can use the Multi-Frequency Field Profile option. You can use the Visualize Data button to view the imported field profile, and the Clear Data button to clear the field data. Click OK to accept the settings. Click the Run button, and after the simulation completes, right-click on the profile monitor and visualize the electric field profile. You'll see that this matches the field profile that we loaded. From the vector plot, you can see that the fields are radially polarized. Here's some useful information for setting up import sources. The data that you load doesn't need to be sampled on the same grid as the simulation mesh, and they can be defined on a uniform or non-uniform grid. The fields will automatically be interpolated onto the simulation mesh, so you don't have to worry about the exact locations where the fields are defined. There are no rotation settings for the import source, so if you want to apply an additional rotation to your source to inject the fields at an angle, one way you can do this is by importing the original field data and then measuring the fields across an angled plane in front of the source. You can then use the data from the angled plane as the data to import for the simulation where you want the fields to propagate at an angle. You might want to use the Angled Monitor Analysis group from the object library to do this. A link is provided below for more information about the Angled Monitor Analysis group. If using the import source to split up a larger simulation region into two simulations, like the case discussed in the previous unit, keep in mind that any light which might get reflected back and forth between the two separated parts of the structure won't be taken into account, so this method will decouple the two parts of the structure. So only use it if you expect that multiple reflection events will have negligible impact on the performance of the device.